Welcome back, Contemporary Math. We are in chapter 7b. So this section is about combining probabilities. So they start off with a sort of anecdotal, historical sort of example. And they open up with that and they kind of end with it. And they open up and it describes this error this guy makes. But basically, they open up with that story, and then we're going to go into combining probabilities. So there are basically two sorts of ways we'll combine probabilities. We will say we'll use the word and or. So this is somewhat, it should be analogous to the things we were doing when we were covering logic. So when we look at and probabilities, there's one sort of question we're going to ask ourselves, and that's whether the events are independent or dependent. So whether they are influencing each other or not makes a difference when we find those and probabilities. And when we find or probabilities, we will talk about overlapping versus non-overlapping events. And then there's one last sort of little thing, the at least once rule we will talk about. And we'll talk about why that applies to the example that they throw out at us. And we will end with that rule. And we will end with solving this sort of little riddle of what did he do wrong. So in 1654, here's the thing copied and pasted from the book pretty much. There's a French con man. His name was Chevalier de something, I don't know French. So I'm probably going to butcher it. Chevalier de Mer. His given name was Anton Gompard. And he bet other gamblers even money that he could roll at least 1 6 in 4 rolls. So he's going to roll the dice 4 times, and at least one time a 6 will come up. He's talking about a standard 6-sided die. We're assuming it was a fair die. And he ended up making a profit. And he didn't. He made a profit, but he didn't calculate his probabilities of rolling it correctly, because the probability of rolling a 6 in one roll would be 1 in 6. So 6 is one of the sides of a die. So if you're doing one out of them, you're going to roll that 1 out of 6 times. And so that is coming from the previous section with theoretical probabilities. There are 6 possible outcomes. 6 is one of them. So he falsely reasoned the chances would be 4 times greater, since he's doing it 4 times, or that would give him 4 6. But in fact, the chance of rolling a 6 is only about 52%, or 0.52 probability, and you would lose about 48% of the time. So it's not as high as he was predicting it, although he still profited. So if he's getting if they're paying the same amount and he's getting larger than 50%, it is in his favor, basically, right? So it is within his interest to sort of play the game. He's going to profit over the long run. He might lose in any independent little trial, right? In any independent trial, but he will win overall if we get enough. If he keeps playing, he will average a profit per game. And we'll talk a little bit more about like expected value and things of that nature, and how to play games maybe a little bit, and what a winning game looks like, and the next sort of units. But this one, and they kind of extend his logic. So if his logic was correct, the probability of rolling at least 1 6 in 5 rolls would be 5 6, and the probability of rolling 6 rolls would be 1, right? And it would be guaranteed that you'd roll a 6 within 6 rolls, which we know isn't the case, right? We can roll 6 times and we can never get a 6. And so that's sort of like what this first example is getting at here. We were trying to prove where his logic is flawed. So if the probability is 1 6 and we multiply it by 6, we're getting 6 over 6, or 1 as a probability. That is what his logic would say. Like if we roll it 6 times, we're guaranteed to get a 6. Here, I want to look at these. So I have a die. I rolled it 6 times, and then I did that and repeated that 10 times. So I do 6 rolls. and then I do 6 more rolls, and then I do 6 more rolls. So I'm rolling it 6 rolls at a time. So I'm grouping them by like each 6 roll, right? And if I look here, this has a 6, this has a 6. I'm looking across here, this one has a 6, this one has a 6. This one has no 6s. I'm looking across, this one has no 6s. This one, ooh, no, that one has a 6. This one has no 6s. And this one has a 6, this one has 2 6s. Okay. So I believe there are 3 of them I put a tick mark next to that I should have. How many times did you not get at least 1 6? 3 times. How many times did you get at least 1 6? That would be 7. At least 1. So this one has a 6. We can count them along, but there's 1, 2, 3, 4, 5, 6, 7 of them that I get at least 1 6. Some of them have 2, but that's all right. Some of them got 3. That's okay. It has at least 1. What do they say about Chevaliers' logic? Well, 3 out of the 10 times, or 30% of the time, we didn't even get a 6. So under this, we should be getting a 6 every single time. Under his logic, it should happen every single time. It should be guaranteed. In reality, when we actually do the relative frequencies, this is only happening 30, this is happening 70% of the times. It's only happening 70% of the time when it should be happening every time. 70% of the time, it happens every time. No. Okay, so definitely flawed logic is what they're trying to get at. He is not figuring this thing out correctly. Okay, so we're looking along here, and we want to talk about and probabilities. And so and probabilities, we're going to figure them out a little differently if they're independent events versus dependent events. So within these words, like even if I didn't tell you what independent dependent means, you know, independent means it can stand by itself, right? It's not going to influence anything else. You're not going to be influenced by anything else. You're standing there independently. And you know, dependent, right? Dependent, one is going to depend upon the other, right? So here, if we have 2 events that are independent, one of the occurrence doesn't affect the other occurrence, right? We have 2 different events. Just like when we're rolling a die, if I roll it, the first roll is not going to influence the second roll. If I'm rolling 2 die, the roll of the first die is not going to influence the second die, right? If I what else do? Flip a coin. If I flip a coin, the first flip is not going to influence the second flip. And there's a few that other events I could probably give that are independent. But I'm sure you could think of a few. And we will talk about dependent and compare and contrast that in the next section on this unit. But if we think about 2 independent events, and they give me this, if I have 2 independent events, the occurrence of one doesn't affect the other. If we want to think about 2 things happening, P of A and B, that's P of A times P of B. This principle can be extended to any number of independent events. For example, the probability of A and B and a third independent C can occurring together can be P of A times P of B times P of C. So we can do this with 2 events. We can do this with 3 events. But if I'm tossing what? 3 fair coins? What is the probability of getting 3 heads is his first question. So I'm tossing 3 fair coins. So I want to think about getting the probability of getting what heads on the first coin, and the probability of getting heads on the second coin, and the probability of getting heads on the third coin is what I want to think about. So the probability of each of these is a half. So if I want to get 3 heads, or the probability of getting a head, and not run out of heat, let's do it. It's going to be this times this times this. And so what this is saying is, if we know the independent probability, we can multiply these together, and we're going to get 1 over 2 times 2. It's going to give me 8, or 1 out of 8 of the possibilities. And so if we go back to, what was that, 7a, we had those 8 different possibilities when we're flipping 3 coins. There was one of them that was heads, heads, heads. There's only one way to get 3 different heads, or 3 heads. It was 1 out of the 8 possibilities, or you could give me 0 point or 0.01. Okay, so what's the probability of getting 4 6s in a row on a single fair die? So we want to do the probability of getting 6, and we want to do that 4 times. And if we multiply these all together, I'm getting 1 over 6 to the 4, 1 over 12 times 6. That's a pretty small number. You might figure out it's pretty rare if you got a fair die that it's going to come up with the run of 4 6s, right? But it does happen. It is one of the possible outcomes. Okay, so find the probability that a 50-year flood, or a flood with what, 2% probability of occurring in a given year, will hit the same city for 3 consecutive years. So the probability it will hit, and they're assuming that a flood in 1 year is not going to influence the likelihood of flood in the next year, which is probably not a good thing to assume, but they're doing it. So in 1 year, there's a 2% possibility, and the next year there's a 0.02 possibility, and in the third year there is a 0.02%. And so we want to know, well, what's the probability it will flood in year 1 and year 2 and year 3. We have to multiply these 3 things together, or it's going to be 0 point, and there are 5 zeros here, 5 and 8. So you probably figured flooding 3 years in a row should give you a really, really small decimal number. Okay. And so that is if the events are distinct independent events, they're not influencing each other. Now we have to think about like a situation in which they might be influencing each other. So these would be dependent events. The occurrence of one is affecting the other. So if we want to know P of A and B, and A is occurring typically before B, first off, we find the probability of A happening. And then since A is influencing B, our probability of B given A is going to be a little bit different. So we're going to have to talk about how we find that, and we'll have a few examples to get at that. But we can do this with two sorts of things. We can do it with multiple sorts of things. We can chain this out just like we were doing previously. And so I want to give an example, and I got a bag of tiles that I'm drawing from an example 5. So if I draw 2 tiles at random from my bag that contains 20 red tiles, 24 yellow tiles, and 16 blue tiles, my total tiles here there are 60 tiles. Get that number out there. There are 60 tiles total that we're starting out with. They're all colored differently. If I just reach into the bag and draw out 2, what is the probability of those first 2 selections? And I'm not going to put them back in without replacement. I'm going to draw them and keep them out. I start with 60 tiles. What is the probability that the first 2 will be yellow? Did not do that right. Okay, so now I want to think about this. So the probability of finding a yellow on my first pick. Okay, so I'm starting out with a total of 60. If I want to pick a yellow, the total occurrences of yellows in this thing would be 24, is the frequency that the yellows are happening at. There are 24 yellow out of 60 total. That would be the probability of drawing a yellow on the first one. I have to do a little bit of thinking on. So out of the total, so if I pick a tile out and I do not replace it, now my total is changing. This is the thing we have to think about. I have drawn one out of them. Now I'm drawing out of 59. We're doing the number of yellow out of the total tiles. Define the frequency of these things. Define the probability that we will draw it out of there. So if I start out, there are 24 yellow tiles out of the 60 total. I draw one out of them. Now I'm down to 59 total. And if I draw one and it is yellow, the next one, there will only be 23 yellow to draw from. So this one has to go down, and this one has to go down if this first one we drew was yellow. So we have to take into account the fact that we drew out a yellow from this thing. We take it into account by subtracting 1 from the total, by subtracting 1 from the number of yellow tiles there are. So now this probability should look something like this. My total number is going down, and the number of yellow tiles goes down. And if I count for both of those, I get a really 552 over 35. They reduce to something like 46 over 295. But the thing I probably want is 0.156, somewhere in that ballpark, right? So maybe something to notice is that we have probabilities that are between 0 and 1. And the more that we keep on saying and the more like things that we keep adding to it, typically the smaller that probability is going to get, right? If we want to know what's the probability that we're going to get a head versus the probability that we'll get two heads, the probability we'll get two heads in a row versus getting one head is going to be a lot smaller, right? The more trials we add to it, the more entries we're going to get, or the more outcomes. So the probability of a single outcome will be smaller. Okay, so a 3-person jury must be selected at random from a pool that has 6 men and 6 women. What is the probability of selecting an all-male jury? First off, I want to do the probability of selecting a male. From here, straight off, the first male, I'm selecting from 12 people total. I am selecting 6 from 12 people. I have selected my first male. Okay, and then I'm going to do the probability that is male given a male. And so on, right? And I have to account for that I took 2 of them out here, is what this is saying. So I selected a male on my first one. So now instead of 12 people, how many people do I have total? I have 11 people total here. And if I selected and I pulled out a male on the first one, how many people are left here? There are going to be 5 males left. I have 12. This is going down to 11. I picked out 2 males. 10 people total left. I have 4 males left. And I have these 3 numbers. I have these 3 probabilities. The way that I combine them when I want all 3 of them to happen simultaneously is I multiply them. So I'm looking along here. I want this to happen and this to happen and this to happen. This should give me 120, 1520. So this might seem like you got 6 men and you got 6 women if I want an all-male jury. And I think I might have ripped this straight out of the book. I don't even think I made change the numbers. And I did that because like you want like everything seems very even here, right? But then I'm asking about selecting 3 males in a row. And so if everything is even, then you should probably get like a pretty even mix of male and female, and that's not happening. And so this is actually a somewhat rare occurrence that it would be all male without a single female, right? Okay. So when we talk about and probabilities, we want things to happen. And remember, and is a very sort of demanding sort of thing, right? And so we're wanting more and more things to happen. We're being very specific. And so our probability is getting sort of smaller and smaller when we use the and. When we use or, typically our set's going to go kind of the other way, right? We're going to get a larger probability. We're going to include more and more things when you use like the word or. And sort of that's what we're getting at here. We got to consider if they're overlapping or non-overlapping. So we're going to start with things that aren't overlapping. They can't occur at the same time is what this overlapping means. So if we think about things, you're going to roll a die. What is the probability of getting a 2 or a 5? You're not going to get a 2 and a 5 at the same time. And that might seem like a silly thing to say. But when we get to the next example, there will be some examples where they can occur at the same time. And so it might add a little bit of context to what I'm trying to say. But this is with non-overlapping events. We just add them together. We add the probability of one, we add it to the other, and we get a larger probability. It is more likely to happen if we do this, right? If I say, what is the probability of getting a 2 or a 5, it's going to be larger than just the probability of getting a 2. But that's a 6 into a 6. So the probability of getting a 2 is a 6. Probability of getting a 5 is a 6. If we add these two things together, we're going to get like something like 2 6 or a third, or like 0.33 repeating, something along those lines. Okay. Likewise, and I will have maybe a counterexample for this when we get to overlapping. But like if we're drawing from a card deck, so this is going back looking at your playing cards, what is the probability of selecting a heart or a spade? So if we do probability of heart or spade, 13 out of 52 of those cards are a heart, and 13 out of 52 of those are a spade, 26 out of 52 are a spade, or half of the cards that we're talking about are either a heart or a spade. The other two are diamonds and clubs, right? Okay, so another way is this: a quarter of them are hearts, a quarter of them are spades, half of them are diamonds or spades, right? We're talking about half the cards if I say hearts or spades. I could say P of heart or spade. I could say P of 2, right? It's going to be a P of 2 plus P of 5. We're adding these probabilities together. All right, so now we want to talk about overlapping events. So if they are overlapping, there is something they have in common. There is an intersection happening here somewhere, P and B. So I think one of maybe the easiest ways to get at this is to look at this. And if you wanted to, you can go back to this example. If I do hearts and spades, so if I circle all my hearts and I circle all my spades, those are non-overlapping circles. That is a set, right? I circle this thing. This is a set. Those two things do not intersect at all. If we look at this next example, what might we notice? If you select a card at random from a playing card, what's the probability of the card will be a jack or a spade? So if I look along here at my jacks, and I look here at my spades, notice they have something in common, and that guy is called the jack of spades. So what I have to do to find this probability? P of jack or spade. Probability is a jack. Probability is a spade. Minus P of So let's look along here. The probability it is a jack. So the probability it is a jack is 4 out of the 52 cards. The probability is a spade is 13 out of the 52. We're going to have to subtract 1 out of the 52. And if you want to look along here, what we're doing is we're including these 13 and we're including these 4. So if I add this 13 and I add this 4, what you might notice is you've added this overlap twice. So if I look along this 13, I add 13 and I add 4, I'm adding this guy twice. So what I have to do is I end up having to subtract this guy. So I'm adding the 4 and 13 gives me 17, and I have to subtract 1. Or I'm getting 16 out of 52. That's 4/13 if I simplify it, or it's going to be somewhere around 0.0678. And so you might notice, and I talked about it, I'm going 4 and 13 and subtracting 1. There are a total of 16 cards that I've circled here. 13 plus this 4, and I subtract this 1 because I double counted it. So if they are overlapping, basically all this says is we're adding them together, and we have to subtract their intersection because we could double counted it. Because if I count this and I count this, I've counted the intersection twice. And so we have to account for whether or not they're overlapping. So like something like this, if you select a card at random, what is the probability it will be a jack or a spade? So anytime you see that word or, ask yourself, can it be a jack and a spade? In this situation, it absolutely can. And we call that guy the jack of spades. If we want to look at that previous one, can it be a heart and a spade at the same time? No, it cannot. So we do not have to care about their overlap or their intersection. Okay, the at least once rule for independent events. So we're assuming these things are independent. And this goes back to that and statement, right? If they're independent, one event is not influencing the other. We don't have to think about doing things without replacement, right? It's like each one of those we can think about separately, and one of them is not going to change the other, right? So suppose the probability of an event A occurring in one trial is P of A. If all trials are independent, the probability of an event occurs at least once, and in trials is, okay. So right here, ignoring this part, this is coming from that previous thing, right? If we add up A happening at least once with no A's happening, it's either not happening or it's happening one or more times, right? And so if we add these two things up, it's equal 1. So if I want to think about the opposite of that, if I subtract 1, this from 1, I should be getting to this. So that is where they're getting this property from right here. If I want at least one event A and in trials, it's going to be 1 minus no A's in trials. So this is the full outcomes. This will describe every outcome that we can, right? Either A doesn't happen or it happens more than one time. And if we add those together, we get 1, we get the full sample set. The other thing is they're saying P of not A. This is like saying P of not A and P of not A and P of not A n times. And so if we say not A, this is all the same probability because they're independent. So we have the same number being multiplied over and over and over again n times. That is the same thing as putting it to an exponent. And so if this was heads or tails, right, the probability of getting not tails would be a half. It'd be a half times a half times a half n times, or a half to the n. So it's 1 minus whatever the heck this probability is to the n. And we are going to use that formula to solve these next few things. So P of at least one head in 3 trials. And so going back, if you want to look at this and you want to go back and look at those 8 different outcomes that we got back in 7A, we're using the at least once rule. So if P happens at least one head in 3 trials, that's the same thing as doing 1 minus no head in 3 trials. That's 1 minus the probability that we're not getting ahead 3 times. So this is equal to 1 minus the probability. The probability of not getting ahead is the same thing as the probability of getting, excuse me, a tails. Which is a half. And I'm doing this to the 3rd power. So a half times a half times a half should give me 1/8. So it appears 7 out of the 8 times, or 0.875. So about 87.5% of the time, you should be getting at least 1 head in 3 trials. Which, if we go back and look at all our possible outcomes, there is only one outcome where we don't get any heads, right? So in 7 out of the 8, we're getting at least 1 head. There's one possible outcome where we don't get any heads. That's all the tails, tail, right? So this should match up with what we were saying previously with our outcomes. Now, we don't want to like follow this sort of thing. We want to sort of generalize formulas so that when we do things larger, we can do things larger, right? We're only doing 3 trials there. So we can do larger trials. You purchase 100 lottery tickets, for which the probability of winning some type of prize on a single ticket is 1 in 20. So this is like the number of trials I'm doing. The winning for a single trial is 1 in 20. What is the probability that you have at least one winning among the 100 tickets? Minus the probability of no win. 100 trials is what I'm doing this for. So maybe I'm skipping a little bit more. I'm going from that first statement to the last statement in my definition. I don't really need that middle guy, to be honest. This is the thing that's going to get me to my solution. So the probability of not winning here. The probability of winning is 1 in 20. So if you're going to win 1 in 20, guess how many times you're going to lose? 19 out of the times. So I'm doing 19 divided by 20. I'm raising that to the 100 power. Gives me like something like 0.005. And I'm doing 1 minus that solution, gives me something like 0.994. And if you purchase 100 lottery tickets, you might have a 1 in 20 chance of winning, but you probably figured out if it's 1 in 20 chance of winning and you're purchasing 100, you have a pretty good chance of winning it. You got about a 99% chance of winning at least one. You probably win your dollar back or something. So you probably spend $100 and win $1 back. Probably not going to do very good. There's a reason why they have lottery tickets. There's a reason why casinos exist, right? It's because it's not because they don't know what they're doing statistically. They know very much what they're doing statistically. And we'll talk a little bit later about expected values of games. And that's what they're really banking on. They're really banking on expected value in sort of this thing called the house edge. So return to Chevalier. So back to that guy, the first example. He wanted to roll at least 1 6 within 4 rolls. So the probability, now that we're getting at this, is the probability of at least 1 6 in 4 rolls. Should look like 1 minus the probability of not getting a 6 in a single roll. And we're doing that 4 times. So this is 1 minus 5 6 to the 4th, should give us that 52% that they were talking about at the beginning. And this will close out this unit. And I hope to see y'all soon. Take care and study hard.